Oh, sorry.
Was me.
Sorry, I hope you can hear me on line 2 now. I was just saying we mostly look at 3 months averages because of the challenges we have with seasonal forecasting, and what's most is that we look at month 2 to 4, so right after that sub-seasonal time scale. That's what I'll be forecasting on. Not to
No, this was the wrong one, I think.
I think now it should work. I hope. Okay.
Maybe use the arrows. I don't know.
Change to laser pointer.
Oh, to like down here?
No. Right click. Option.
Yeah. Okay. So on seasonal timescales, forecasting is challenging. You can see on the left for the mean sea level pressure forecast done with the DWD model for the winter season, forecast that started in November. And there's good skill over the tropics, especially over the ocean, also over the North Pacific for sea level pressure forecasts. But then forecasts get more challenging as we move into North America and to middle altitudes, North Atlantic, and then especially over Europe. We basically have very little to no skill for mean sea level pressure forecasts for the winter season with the DWD model here. But if we look at other variables, this is now specifically for Germany. If we look at 2 meter temperature, we do have some skill. So again, for the winter season, we get values for the ACC between 0.4 and 0.6. So this is pretty good skill. If we look at wind speed forecasts, and this is from a recent study that looked at wind speed forecasts in the US for, again, the winter and also the spring season, you can see that for the winter, we have some skill over the western US. And then for spring, there's a really good skill actually over the southern US. So that gives us hope that we might also have some skill in forecasting wind and solar radiation for Germany. The data that we use the DWD hindcast from the GCFS 2.1 version last 31 years. And we have a downscaling method called episodes, where we bring the global model forecast to a higher resolution. We do that specifically for solar radiation and wind speed. We also use the ECMWF and Meteor France model hindcasts, slightly different model period that was available, and we also downscale these forecasts or hindcasts with episodes. Furthermore, we have a subsampling to create a smaller sub-ensemble. So we pick out ensemble members from our full ensemble, create a smaller ensemble. This is based on SSTs and the large-scale circulation. We have a current version of the subsampling in revision. So if you're interested in more details, you can read about it here. We use 2 data sets, the HIRIS and the ER5 reanalysis data set to calculate skill scores, do verification, Yeah, with that, I'll show you some results. This is now for, again, the winter season. DWD hindcast forecast to start in November. And for the full ensemble, the anomaly correlation coefficient compared to the ERA 5 reanalysis. And we actually do have some skill, like it's around 0.3, 0.4 for Northern Germany. It's not super high, but it's similar to what we saw for the US in the other study. If we do that for the subsampling, so here we pick out 10 ensemble members in each of the hindcast years, we actually have a nice skill increase. We have skill between 0.6 and 0.7 for Northern Germany, so we're quite happy with that. We then try to understand where that skill is coming from and what that looks like for the individual years. So you can see here on the left, the forecast for the full ensemble for all of Germany, so it's average over all of Germany now, for the winter season, so again, a 3-month period. And on the right-hand side, there's the subsampling. So again, only 10 ensemble members. We have a pretty large spread in the full ensemble. We have an ensemble mean that's around 6.5 to 6.7. We have a shift in the distribution to higher and lower wind speeds in some winters, but in general, you can see the challenges of seasonal forecasts in this plot. Some years like 2010, we expect lower wind speed values. Other years, we have a shift to higher wind speed values. If you look at the subsampling, we have stronger signals, stronger shifts in the whole distribution. For example, in 1995, we have a strong shift of the whole distribution to low wind speed values for the winter season in Germany. Other years like 2019 here, we have a shift to higher wind speed values. If we then include the ERA 5 reanalysis, here for the full ensemble on the left, then you can see we have like 3 different winters in Germany. We have some winters where we have relatively low wind speeds, on average around 5.7 meters per second. We have some winters where we have relatively high wind speeds, up here 7.5 meters per second, and some winters that are in the middle. And with the full ensemble, we can capture this, like the full ensemble spread capture, except for 1994, where we miss it completely. Otherwise, we can capture it, but you can also see the challenges because we only sometimes see a shift of the distribution. For the subsampling, this works better because we get the tendencies better, like 1995 was actually a really good forecast, where we almost capture the ERA 5 reanalysis value with the forecast. And that's why we also get the higher correlation skill because we get it right in lots of years. In some years we miss it completely, or we have the danger that we have a small ensemble spread and the ERA 5 reanalysis value could be outside of that ensemble spread. I want to quickly focus a little bit on that year 1995. And I'll show you here the 3-month period from 1st of December to end of February. This is now the ERA 5 reanalysis for daily 100-meter wind speeds for Germany again, so average. And what we saw before was basically the mean for that winter season, which was relatively low. You can see it compared to the 30-year mean in the red dashed line. And you can see there's quite a bit of fluctuation. Like on average, we're below, but we have some days or some episodes like here in February where we have higher wind speed values, some episodes where we have lower wind speed values, quite a bit day-to-day fluctuation. But on average for the 3-month period, we had, and you can see this here in the plot, we had high geopotential height anomalies, positive geopotential height anomalies over Northern Europe, from Greenland over to Scandinavia, and we had negative potential height anomalies here over Southwestern Europe, and Germany is right here in the middle, but that can give you an indication why we had relatively low wind speeds for Germany. And if we look at the forecasts for the geopotential height field in our subsampling here on the right, you can see this is now for the individual months, so it's not exactly the same, but it gives you an indication that the subsampling could capture some of the circulation that we at the end saw in the ERA 5 reanalysis pretty well. So we have here for December, high pressure anomalies over Greenland, then more shifted towards the East Atlantic, and then again over Northern Europe. So there was a signal that the subsampling could capture. And this is also reflected now here on the top left again. I include the subsampling forecast for the individual days. Then the subsampling ensemble, basically. You can see that, again, the day-to-day forecast is very challenging to do. Can't do that on seasonal forecast. That's why this doesn't fit. But the 3-month period was really well done by the subsampling. But we can't do the day-to-day. What about monthly? We saw this yesterday in Alberto's talk that we come from 3-month period, but sometimes we might be interested also in monthly forecasts on seasonal timescales. So we tried to do that also for the winter season. This is again forecast to start in November, for December, January, February now individually. And we can see for the full ensemble, if we look at December, we still have some skill over northern Germany. January and February is then more challenging and basically no skill. But if we look at the subsampling, again, here for the individual months, we have fairly good skill for December and still some skill for January and February. So we might also be able to do with the subsampling forecasts for these individual months. Now, I'm just going to show quick 2 slides about solar radiation forecast. This is now for the summer season, so forecasts that start in May for June, July, August. And again, the ACC here for the full ensemble forecast, you can see that the skill is lower compared to what we saw for the wind speed for winter. We only have a little bit of skill over southern Germany, basically no skill over the northern half of Germany. But if we do subsampling here again and pick our 10 ensemble members in the hindcast period, we see a nice skill increase, especially over northern Germany. Over southern Germany, skill is actually a little bit lower than compared to the full ensemble. And again, quickly, the time series. You can see similar things than what we saw for the wind speed forecast for winter. We have a large ensemble spread. Only in some years, we have a shift to higher and lower solar radiation values. But with the subsampling, we get stronger tendencies. For example, here 2020 or 2018, we have signals for high solar radiation values for the summer season. If we include the high-res observations, and see the full ensemble struggles to capture that most of the time. For example, 2003 is missed. We don't see a shift in the distribution, or 2018 or 2019. Where we have high solar radiation values for that summer season in Germany. The subsampling in general does a better job, like 2018, for example, we see that signal. 2019 again was not well captured, and 2003 also was not well captured. But years like 1998, where we had low solar radiation values, that was in the forecast. And with that, just want to show you what we're currently working on. We currently look at multimodal forecasts. So instead of just looking at the DWD hindcast, we also look at ECMWF and Meteor France. This is now again for 100-meter wind speed forecasts for the winter season. And we also do a multimodal forecast where we, in the first step, just combine all the ensemble member from the 3 models. And you can see that Meteor France hindcasts are similar in terms of ACC compared to the DWD hindcast. ECMWF for this lead time is slightly worse. And the multimodal is also similar to DWD in Meteor France. And we then also do a subsampling for the 3 models individually. So one subsampling for DWD, one for Meteor France, and one for the ECMWF. This is now a slightly different hindcast period where we had the data available. And we do a subsampling also for the multimodal, so where we pick our 10 ensemble members for each year out of the 80 that we have available in total. And you can see again here we have a skill increase compared to the full ensemble, but the multimodal is not necessarily better than the individual models. And lastly, this is what our newest setup so far. I've shown you a multimodal subsampling based on so-called targeted teleconnection on temperature. And we aim to do that right now also directly based on 100-meter wind. And with that, we actually get a better skill than just than what we are using before. And we're currently looking into that in more detail. And with that, I'm at the end. I hope you can agree that we have some skill in doing seasonal forecasts for 100-meter wind speeds. I showed you the winter season. Other seasons are more challenging in general. But for the winter, we do have relatively good skill for Germany. We have a large ensemble spread for using our full ensemble, just given the uncertainty that we have. In some years, we have a tendency for higher and lower wind speeds. With the subsampling, we have a better skill, and we also have a better tendency for higher and lower wind speeds in most winters. But we also have a small ensemble spread, and then the risk of missing the reanalysis value completely. So solar radiation forecasts in summer are generally more difficult compared to the wind speed forecast in winter, but we see also some skill with the subsampling here. And our current multimodal analysis shows that we have, in general, similar skill compared to the individual models, and we have some new promising results with the new targeted subsampling approach based on wind speed directly. And in the next while, we want to focus more on weather regimes and teleconnections, and hope that we can learn some more about the forecast, potentially improve the forecast. And yeah, with that, I'm at the end. I'm happy to hear questions or comments. Thanks for your attention. And I don't have Slido questions, unfortunately. I'm sorry.
Thank you for your presentation. When you were validating the 100-meter winds, if I understood correctly, you're using year 5 as your ground truth. I just wondered, of course, you wouldn't have as many data points, I suppose, across Germany, but you thought of maybe using the sounding data throughout Germany to at least verify against?
Yeah, we thought about using other data sets for the verification too, but given that we are on seasonal timescales, we took the ERA 5 as a good first guess. We know that there are better data sets out
also, there. ERA 5 assimilates sounding data.
Yeah, yeah.
So I was wondering about your subsampling. How did you decide to select 10 ensemble? Because that's kind of tricky. In the instances where you validated it perform well, but with this subsample will be as accurate in other instances.
Mm-hmm. Yeah, I didn't do the subsampling, but basically how it works is we look at large-scale circulation, MSLP fields, and then this is specifically targeted at temperature for Germany. So there's like a correlation established in the historical data set. I think AR5 was used. And so from that, we basically learn a connection between the large-scale circulation and temperature that is not necessarily represented in the seasonal forecast model. And with that, the forecast members are picked out. And this can also be done in a future operational setup. And for that, we use the connection between SST and MSLP. Like on seasonal timescale, there's a strong connection between the SSTs, anomalies, and the MSLP forecast or the circulation that we can expect then. And so from the SST to the MSLP and then targeted at temperature in Germany, that's basically how the subsampling works, and then picks out the 10 ensemble member that come closest to that connection using partial least squares, like a mathematical approach.
They don't have any difference, so it's the same resolution, it's the...
Yeah, exactly. It's just 10 ensemble members.
Everybody can hear online.
Yeah, I was saying if something in the subsample is the models, they don't have any differences in resolution.
No, they're all the same. We just picked from the 30 members that we had in the hindcast, we just picked 10 for each year differently.
Can I just follow up, because I had the same question when you gave this talk at the MS.
Yeah.
So I'm happy to hear some of the answer now. So basically doing this at initialization time, right? So basically, are you doing, whenever you run, it's all hindcast, but let's say you try to pretend you run a forecast by using hindcast, and then at this initialization time, you always, do you do it once, or always at the initialization time that you check which of your ensemble members are kind of the most correlated with whatever your target variable is?
Yeah, so there's a general connection established, and then there, if I understood it correctly, and then for each initialization you check, and you can also do that operationally or in the future, and for that you need the link between the SST and the MSLP fields. Yeah, don't know if that answers your question. So a little bit.
I also have a question, and this is, are you then in the initialization using kind of an analysis also for the boundaries ahead?
No, you use
So,
the
because it's different if you run in handcuffs,
Yeah.
you can make the boundaries better
Yeah.
than if you are in real time where you don't know the future.
no, you use in real time, you use the SST fields from the month prior. So right now, if we have forecasts to start in October, we would use the SSTs from September, and then from that from that SST field in September, you then pick the 10 ensemble members that you need for your forecast in October. Yeah.
I don't know if I have time for one quick question. Can you say a bit more about how do you intend to use the teleconnections in your outlook in the next steps, if you can?
Yeah, we have lots of ideas about that. We don't have something concrete that I can tell you right now, but we have the NAO, we have the ENSO, we have other teleconnections that are important for seasonal forecasting, and we like to understand a little bit more about what impact they have on the forecast, and if we can learn something from it, and then we can hopefully improve the forecast too. But yeah, there's still lots of ideas and nothing like concrete set in stone at this point. So we're pretty open about that.
Okay, thank you very much. Our next speaker is Alberto Soret from the Barcelona Supercomputing Centre, and he's going to talk about seamless climate information for enhanced energy system resilience in Spain. And Alberto is online.
Yeah.
Okay. Alberto, you have to unmute yourself. Or to click on.
Yeah. Yep. Yeah.
Okay. Can you say something? Hello? No. Yes? Yes, now we can hear you. So now you can share your screen.
So maybe you should.
Yeah.
Das ja ausmachen, ich das bekommen wird, wenn wir sehen.
Okay. Can you see the screen now?
Yes.
Okay, perfect. So I cannot see you, but I guess that now I can start, right?
Yes.
Okay, perfect. So thank you. My name is Albert Soret. I work at the Barcelona Supercomputing Centre in their science department. And together with some colleagues from BSc, we are working in two different projects aspects. It's a coordinated project. It's a European project that I coordinate, and also then a national project more focused on energy. And a key task in both projects is to explore different methods to combine different systems. Okay, so now in the community, people is working at subseasonal, seasonal, maybe also decadal projections, and the objective is to put this information together. Okay, so a bit of context. So we are aware about this climate variability. That's why it's important to have information weeks, months, years in advance, because it has an impact in different decisions in the energy sector. More specifically, our main focus is here in working with climate predictions. So working with subseasonal predictions, seasonal predictions, decadal. And as I mentioned, the objective of this presentation is to present some preliminary results about the combination of all these timescales to be able to improve the predictions. Why? Because in the end, there are different sources of predictability, and the objective is to take advantage of all this information into the system. So let's start. So here, what we can see in this figure, it's for 2023 in November. We have the seasonal forecast, the red line. So it's forecast for 7 months ahead. Then the observations in black. And then we have also the decadal prediction. Okay, the decadal predictions are initialized in November and they start to be available around May. So it means that in November 2023, we will have the past decadal predictions in green. We have the observations, this part, and then we have this red line. And we can see that this is, for instance, for the prediction of El Niño index, that there is some agreement between the seasonal and the observations. We see that there is a bias with the decadal, but at some point we will not have anymore this seasonal forecast, and then we need to rely on this on the decadal predictions. Okay, and it has different implications. The first one is this inconsistency, because we are jumping from one system to the other, so it implies that there are these jumps and this lack of coherency, let's say, like this, along different time scales. And also the second one is that we can see that here in seasonal predictions have a higher skill, but the skill for decadal it's limited. So the main research question here is, let's see if we are able to work with all this information, also with the observations, to be able to improve this workflow. So in this case, I will focus on the improvement of the decadal predictions, but we are doing similar work for sub-seasonal and seasonal. So with decadal predictions, now we have 6 operational models, 76 members, and our objective is to reduce the ensemble members to 30. How? The first method is to analyze recent observations. Okay, so to analyze the last observations, and we are doing different sensitivity analysis, working with the observations of 4 months, 3 months, 2 months, 1 month, to be able to do this ensemble member selection. And the other method is that in this case, instead of working with the observation for this subsampling, our objective is to work with the seasonal forecast. And again, we are doing different sensitivity methods to see if it's better to work with only 1 month, 2 months, or up to 6 months of the seasonal forecast to tailor these decadal predictions. Okay. Another key advantage is that decadal predictions, as I said, they are produced once a year. They are available in May, okay, but they are initialized in November usually. But with this kind of methods, what we can do is to provide updated decadal predictions during the whole year, because we will have the observations and we will have also seasonal predictions. So let's see an example. Okay, so this is the skill for different predictions. This color is the historical simulation, so climate projections, to see that we don't have any clear signal. Then the decadal predictions in green, and here we have the skill for the seasonal forecast. So when we apply these methods to combine these systems, what we see is that we have 2 different results. The first one is that these ensemble predictions using observations in blue and with seasonal forecast in purple. And what we can see is that these predictions are able to reproduce the skill of the seasonal forecast at the beginning of the simulation during the first month, but then there is a decrease in the skill, but the skill is higher compared to the predictions from the decadals. Here we have different results for depending if we work with observations or with seasonal forecasts, but there is a clear signal that we are able to improve the skilling during all this period. Okay, so now let's come back to the figure that I was showing at the beginning to show how we can see it in terms of forecast. So again, these are the observations. Then we have the seasonal forecast, 6 months ahead. Then these are the decadal predictions, and this is the mean of the ensemble system, combining the decadal and the seasonal, and we can see how the evolution of the seasonal and the seamless are similar to the observations, but then when we don't have when the seasonal predictions are finished, we continue having this information, and we can see the difference between using the raw decadal predictions compared to these seamless predictions and the comparison with the observations. Again, this is for El Niño index. Okay, so this in terms of applications for the energy system, we go to go further. Okay, but I think that with this figure, it's easier to understand the methods. Okay, so now let's see how to apply this for the energy sector. Okay, in this case, what we have been doing is combining the subseasonal and seasonal predictions in an hybrid model, working with different larger scale patterns to be able to select the best ensemble members. Okay, so in the end, what we get is an hybrid seamless predictions for seasonal and subseasonal, seasonal and decadal for wind speed. And these are part of the preliminary results that we got, okay, in America, and we can see that in the rate areas, that some of them are compatible with locations that are critical for the wind energy industry, that we're able to improve and to have a skill, because the skill for wind of the raw predictions is quite limited. So in these figures, we can see that there is a significant advantage of this method. But as I said, so these are preliminary results, and we need to continue exploring this. Then also something that we are doing is transform this into indicators. Okay, so in this case, well, this is a parallel work. So in this case, it's only now with decadal. So we are converting the wind speed into capacity factor. We can see this is for Europe. We can see the wind capacity factor for a specific turbine, the intensity in Europe for the different seasons in the year, and we can see also the level of skill of the simulation. Unfortunately, as I said, so the wind speed for directly from decadal predictions, the level of skill it's limited, so therefore the translation it's also limited. But there is some work here to do to combine both methods, so the seamless predictions with this translation into tailored indicator for the wind energy. And yeah, here well, some of the results showing that there is a decrease in the multimodal in most of the period, and we need to better understand this decrease in the wind speed. And then finally, also something that we are doing is focusing in some specific events that affected the energy sector. So for instance, together with our colleagues from EDPR, that I think that Alberto it's there in the meeting, we were discussing critical periods of the past that are relevant for the energy industry to analyze the reasons behind maybe the seasonal forecast, we were not able to produce proper forecast. Okay, so in this case, we are focusing this area in Brazil for January 2025, that there was a significant wind drought, and this was a period that usually the wind energy production it's quite significant. Okay, and if we check the forecast, we see that the signal it's quite different. Okay, so our objective here was to analyze this period and then to compare it with past events and trying to analyze the drivers that are leading to this situation. Okay, so here's what we did is to identify the anomaly for this January and compare this anomaly with previous Januaries. Okay, so here what we can see it's the anomaly for wind for the different Januaries in the last years. Okay, so to identify those periods that had a similar behavior in terms of wind, to be able to analyze the drivers for those periods too. Okay, and what we can see is that, for instance, if we compare the wind anomaly in this area, okay, with the sea surface temperature, okay, so here this pole that we see here with a lag of 1 month, 2 months, 3 months, etc., we see that this system is consistent for a significant period. Okay, and this is the kind of things that we are trying to do. So to identify the systems that are related to a specific anomaly, and to see also if there is some delay between the driver and the final signal. Okay. And thanks to this work, so what we identified is different systems in the tropical Atlantic, but also in the Pacific, like ENFOR, that are affecting the anomaly of wind. And now what we want to do, and this is something that we are working on now, it's to understand, to have a verification or forecast quality assessment of the different seasonal forecasts, if they are able to properly reproduce these systems that in the end they are related to the situation, to the wind anomaly here in this area. And this work it's complementary to the previous one that I was mentioning about providing these seamless seasonal and decadal predictors, because in the agri modeling we are also using part of these systems. And that's all with this presentation. So as you can see, so there are many things that we are still exploring and trying to see how we can be relevant for the energy sector. But these are 2 projects that are running. And for instance, within the context of the Boreas projects, we are going to start organizing now climate outlooks to review past events and to analyze future forecasts and to discuss part of the results. So if anyone wants to be informed and engage with us, feel free to send me an email and we will let you know about the results. Thank you.
Thanks, Albert. I think the task in itself is interested in hearing about the project. So we will definitely be in touch. So are there any questions?
I have one question. Can you hear me?
Yeah.
It's on. Sorry. So I know about the project, but just to remind a bit. So when you select the members from the decadal simulations that perform best at the beginning of the season, I didn't understand how you did combine the seasonal and the decadal simulations. if you use the seasonal simulation just to know what the best reality is or the best models are.
I don't know if I probably understood the question, but I guess that how we perform this selection of the
Yes, how you perform the selection of the members.
Okay. Yeah. So what we do in this forecast, we analyze the specific patterns and we select those members from the decadal that are more aligned with the signal of the seasonal forecast. Yeah.
So you don't decide based on observations, but on the seasonal forecast.
In both. So we're comparing different methods. So in the first one, what we do it's to use the last observations, okay, for instance from ERA 5, and we compare the ensemble members from the decadal with these observations, and we select a subsampling of the models of the members that better reproduce the observations. While in the other case, with the seasonal, in this case, what we do is we analyze the ensembles of the seasonal forecast, and we compare the decadal predictions, and we select those members from the decadal predictions that are more aligned with the seasonal forecast.
Okay, understood. It's clear now. Thank you.
Thanks. We're about to publish a paper soon, so it's in revision, but hopefully in the forthcoming weeks it will be available.
Thank you, Albert, for the talk. Very interesting results. I was wondering, so in the case where you compare the decadal members with the seasonal members, so imagine there's this overlapping window of decadal and seasonal where you can somehow compute how similar they are, but I was wondering what happens after the seasonal forecasts are over. Do you keep the same members that you selected for the seasonal time period, or do you keep the entire ensemble, because the same selection of members might not necessarily guarantee scale beyond that horizon?
Yeah. Yeah, what we do is to maintain the same members, because what we are assuming here is that those members that are better initialized or that are more similar to the observations are those that are going to produce a better forecast. That's why we see this difference between the raw decadal predictions and the seamless predictions.
Okay, if you don't have any more questions, then thanks, Albert.
Thank you.
The next speaker is Angela Meyer from EEA Delft and a second publication.
Just a moment.
Do you want to have it down here? Do you say next slide? No, one of them. Okay.
Should be sharing, but no, I need to click press share.
Okay. How do we get this?
Maybe I should do that. Let me see.
No, that's
Now we don't need the speakers there. Yeah.
Okay, so now it should work, huh? Good, yeah, thank you. I am very happy to be here. Really enjoyed this afternoon and this morning. So just a brief introduction. So this work, I'm presenting work of a bunch of people, especially Luca, Paul, Francesco, maybe, and also Anna. And So just a rough, it's not a beautifully elaborated presentation, just some mostly unpublished results, which we are going to publish pretty soon. So just rough tour of what we're doing in some of our projects. So this is a project on solar radiation forecasting, which we also discussed previously. So there was someone interested in this from this mission grid operator. So what we're doing here is basically what we're interested in is obviously a very different time scale, right? Not sub-seasonal, but more of minutes to hours, but getting longer and longer. And what I really enjoy about these projects is they are basically not making any assumptions, no parameterizations, no heavy Fortran code, but this is just basically satellite-based modeling. And we do, as you can see here, there's Meteosat. You should see the mouse, I guess. Yes, so that's we use in this case the Meteosat satellites. The radiance is actually, retrieval involved in there. Basically, just what the radiometer measures there, the different channels, and then we are forecasting this to minutes or hours ahead. And it works. I mean, in a nutshell, these models, of course, they have no physics in there, but they are learning and getting better and making progress, right? But they have several advantages, and I'll show you this in a few slides from now. They have several advantages compared to very good physics-based models like the IFS, for instance. One is obviously they are much more real-time, right? So we get the satellite data with a delay of only 12 minutes, basically, or 10 minutes, right? That's from the moment when this radiometer in orbit measured those intensities, let's say, right? 12 minutes afterwards, we can make a forecast. That's quite nice. And it is basically taking the most recent information in, right? There's no, this is from last week, like from yesterday. So we have the actual measurements. That's quite nice. That naturally, of course, gives already an advantage, as you will see in a moment, compared to more physics-based models, which only have data estimated every few hours, I think like 4 times or so per day. So that's one advantage. Second advantage is they are also by nature quite high resolution, because these Meteosat satellites, they provide higher resolution than your, tend to provide resolutions of like on the order of 1 kilometer, which is quite nice. So what you can see here on the right-hand side is an example of a forecast. This is the actual forecast in kind of converted to what it would have looked like from the orbit. Let's say this is geostationary, right? So we have round-the-clock images, and here on the left-hand side you can see examples of what our forecast model does. These are basically just, let's say, computer vision models. So the kind of classical computer vision. We have done one project 3 years ago on where we have kind of used an existing computer vision library that's based on optical flow, where you kind of evolve the clouds forward. But you can also use generative models, for instance. We have published this. If you're interested in it, it's open source, open. Here on our GitHub, so you feel free to have a look if you want. Then there's another model, or let's say another aspect of another project, and what you see here is Switzerland basically, and this is converted, so basically not radiances, but this is converted to global radiation now, which we use as a proxy of what PV producers might need, even though of course they are interested in individual, PV panels, they don't take global radiation in, but specific wavelengths, but still. You can see a video here over the course of the day. So this is a loop, as you see now, the sun is going up, and you can see how this is moving over Switzerland. There's clouds in there coming from the west. You can see sometimes waves in these clouds. You can see convection, and you can see interesting things. Unfortunately, I cannot show you the most interesting part, because I have to cover it, which is basically below this. There's a second figure. Just imagine that there are lots of PV panels, basically, and we have quite a strong non-disclosure agreement, but we are kind of now preparing an application where, which will be out very soon, where you can see the same patterns in your PV fleet of your country, which that's pretty cool. You can see basically, that's maybe not so surprising to grid operators, but you can kind of really see how waves of clouds, for instance, how they move over the PV, installed PV capacity of a country. It's been pretty nice. But I can't show it to you now, but we publish it soon. Good. And then there's also this second row there, the blanks in the middle. This is also something I had to blank out, but you can see at least the aggregated PV. So this the thing at the bottom here, the red dot that's moving there. That's these are different events, let's say, because this workshop is about extremes, right? So the one in the middle, for instance, it's a loop again over several days that we picked from past years. And this one in the middle, you can see it's 5 a.m. now here in the middle, and then the sun's coming 6 a.m., right? And at some time here, there's a cloud, like clouds front is coming from the west, and within 1 hour, basically, it's kind of shutting down most of the PV in Switzerland. That's quite nice, and we have been looking and are now working on this for such ramp events, let's say, in PV. You can see this here in the lower part. We are showing basically the aggregated PV from the panels that we have production data from, which is a significant fraction. And you can see basically how, yeah, this is in a way the ramp event. I mean, according to our definition, I'm very happy to hear your thoughts that there's different ways of defining this, right? So here, what you can see, this ramp is interestingly quite early in the morning, because that's when the probably cold front, I guess, comes in with the clouds, right? And you see it at its peaks, the PV production peaks at 10, and then you have basically the clouds are you would in principle have the daily cycle, right? Like if there were no clouds, this would go up much, much longer and somehow peak here at 12:30 or so. But then the clouds are basically shutting down all of the PV, most of the PV in Switzerland. That's quite a nice case. Yeah, so there's just some nice movies. And then let me just move on. Yeah, so what we have been doing is now taking this event that I've just shown you, the one in the middle, and use different models, data-driven ones, like the one I've shown you before, the ones that you can get from GitHub and they're open, and compare this basically, and compare it to the IFS, see which of these models can get kind of more accurately capture these events. What you see in the upper left panel is the ground truth. So what actually happened, let's say, in that day, the clouds moving in front, coming from the west and moving over Switzerland and shutting off the PV in 1 or 2 hours. And then you can see some data-driven models, like the Nowcast models, let's say. This one here, Shadecast, and then we have also IrradianceNet. This one's also, and then basically these four, right? These ones, Solar Steps, these two here, and then the upper ones. And if you compare, let's say this one in the middle, Solar Steps here, for instance, it gets, I mean, it looks a little bit Van Goghish, right? It's not completely physical, but you can see how it gets the main feature, the front, basically, relatively accurately, right? It just picks up the cloud motion, and that's in the end what you want if you want to aggregate PV. If you're not interested in a single plant, but in like more large-scale aggregated patterns, then that's a really nice feature. Interestingly, we wanted to, and I've just seen Dominic from MeteoSwiss in the call. Hello, Dominic. We wanted to compare this to regional weather forecast models. Been in touch with DWD. They were very kind. Unfortunately, they only store the last 1.5 years of data, so that was not very useful for this case because it was not included in the last 1.5 years. We also wanted the model, so they were not available. MeteoSwiss, in contrast, had the data, but did not provide the data to us. So I cannot share, I give a comparison here for various reasons. Sometimes we don't provide data because we're busy or whatever the reasons are. So, so I can only share the comparison with the IFS, ECMWF model, and you can see it here in the right column in the middle. This is the IFS if you take it as is, without any bias correction downscaling. And you can see very closely if you compare this red box here to the IFS down there. You can see that the IFS is pretty stationary. That's because it's updated only rarely, right? It's kind of just a few times a day. The second feature that you can see is coarser resolution. And then also probably related to that, it's much more blurry, right? You cannot see the sharp front. You just see like, okay, I mean, not trying to bash IFS, it's a very good model, right? But then it's a bit of an unfair comparison, of course.
we try to make it be a bit fairer, so we also bias corrected the IFS, so basically adjusted it to Switzerland, and that's what you can see in the lower corner, but still it does not get sharp features, basically, right? It's not that the kind of model that you need in this situation, in a sense. Okay, good, let me just move on. Yeah, so these are the models. We are going to write this up, and it's going to be published soon, in just months or so, then you can have a look. These are the models we compare, and then yeah, there's lots of data. Just maybe, so just to tell you, we have compared the models with two different target variables, let's say. One is on the left-hand side, you can see comparing basically different error metrics and compare them with regard to solar radiation forecasting. On the right-hand side, you can see different target variable, like compare those models in terms of how well do they perform when it comes to forecasting the PV, basically, in different sites. And that makes quite a difference, actually. That's quite interesting to see. Yeah? So generally speaking, you can again see that, and also the metric information makes a difference. Whether you look at a root mean square error or CRPS can have some implications. And if you aggregate all of this, you end up with something like this. You have lead time here on the x-axis and metric of your choice on like your CRPS, for instance, on the y-axis. And you can see that the IFS models, they start off with relatively high, I mean, as you would expect with such a blurry forecast, let's say, they started with relatively high values, but then the slopes are smaller, basically, right? The error grows less quickly, let's say. Or in other words, the Nowcast model's errors grows faster, right? And then the question is, when do they overtake each other? Where's the cut, basically, right? So you can see this here after something like 80 minutes or so is when, with these metrics, at least the IFS models get better than these forecast models. And all of this is publicly available, so feel free to make use of it. Yes. We are doing similar things with PV in terms of the PV as target variable and writing it up in now. We also have like, yeah, that was my part on PV and solar forecasting. But we also, maybe just 2 slides, we also do other things. We have one project on offshore wind nowcasting, which is pretty nice over the North Sea. And also a subseasonal forecast project that we're in, just so in case someone wants to discuss yeah, one of these things. Huh? Good, thank you so much. Yeah, please. Yeah.
It's like for the mic.
I do have an offer for the verification part. Because the Austrian model more or less covers Switzerland. And the analysis data set covering 2012 to 2022. Yeah, if I'm not mistaken. And it's an ensemble analysis.
Sounds very good.
And then we have our own nowcasting model, as I think you know, so we should also make a comparison of those two.
Yes. I really like that because, you know, I understand that, yeah, it's good. Let's be in touch.
Yeah, because it really does contain Switzerland, and with 1st of January onwards, we have our 1 kilometer model called Alpe Adria domain.
Yeah.
So that has all of Switzerland plus down to the south of Croatia with 1 kilometer resolution.
Wow, sounds good.
And that's almost, so we should have plenty of data set for verification here.
Yeah, sounds good. Thanks.
Hey, thanks for the talk. Could you comment a bit on the actual architectures you use for the deep learning?
Yeah, so I mean, so the maybe I should show this again, but so we for the let's say non-deep learning models like an optical flow library. So the deep learning model that we have was like a diffusion model, a generative model that. But then, I mean, we also have seen, I should say, that maybe it does not matter that much whether you go with a diffusion model or transformer or some other architecture. I think it's maybe a good idea to try out different architectures. And an important lesson is, in any case, to, I mean, you would like to reduce that information, first of all, that you have, right? That's one thing that they call this encoder processor decoder architectures. Like you have some sort of way of sort of autoencoder that condenses your information, then you do the processing in the reduced space, for instance, like a forecast, and then you kind of decompress. That's the overall idea. My impression was that it maybe doesn't matter too much. I mean, there are also other, we're not the only ones doing this, and others have used transformer architectures, for instance, and that also got good results.
Yeah, thanks. A question regarding the reference, the solar surface irradiation. Did you derive that yourself, or did you use a satellite-derived product?
Both, actually, both. So yes, there are products, and we have used one. There are several products, one from the German Weather Service, one from the Swiss Weather Service, but also others. And then we have also emulated this and improved it. We haven't shown the results of that here, but you can, it was, I don't want to say easy, but you can kind of nowadays, I mean, if you have the data, you can basically build a machine learning model that does such a retrieval, basically that takes the same inputs, gives the similar outputs. And what we've shown, if you're interested, I can show you, or you can find the paper in our websites. You can even improve those retrievals. That's an interesting part. So it was a bit unexpected. So they don't just, the machine learning models, at least what we have seen, they don't just emulate and do the same biases, but they can also get rid of some of the biases, which is quite nice. So we, for instance, for the solar radiation, low radiation data sets, here from DWD, it is known, and we've shown this also and quantified this, it has huge biases in challenging terrain, like in the Alps, for instance, or in particular, massive biases. I mean, so big that in the beginning we couldn't believe our eyes because we thought we had done some mistake. And the model, interestingly, does not reproduce that. So it basically does the emulation, does pretty well, but the biases it gets rid of. That was quite nice. You can kind of use ground observations and improve your model, and it's quite cool.
Well, first, thanks for your presentation and for making your model available. And my question is, okay, you made a comparison of your irradiance forecast against weather forecast model, but why not using the satellite images to improve the forecast of the weather model using data simulation to have a longer range forecast horizon?
Yeah, that's like a bias correction, I would, or is it, or like a new, what exactly, do you have like a bias correction in mind, or would you like to use it for a new?
To improve the initialization of the weather forecast model.
Yeah, you could do that, but then you would also have to run the whole weather forecast model. We could do that in principle, like some.
You can do some cycling exactly at the time where the satellite image is available. You rebuild your initial condition, and then you start from this initial condition to produce an improved forecast.
Yeah, it just requires that you also initialize. I mean, that's of course the idea that many people are thinking, right? You need to initialize your model, right? And that's
yeah, but another
run it also.
Another idea would be, and that's what I'm always missing, is that why not using the output of a numerical weather prediction system and then improve it, like aftercasting, or what you call it, or after a post-processing, where you can use the information that you have online, or easier than in a post-processing step. Then you could extend the improvement, or you can get rid of at least the first few hours where the model is not in balance.
I'm not sure I understood fully. Is it like some bias? Maybe we should discuss later. Is some bias correction that you do basically while the data from the AI?
I'm asking whether why you're not combining the input from the weather model with the satellites, and just comparing it. Just do it also with the physical information, because after you said 80 minutes or so, the numerical model gets better. But this is because in the first hours after the initialization, a numerical model is not in balance. And it would maybe be an idea to use your methods to then bring it into that balance, and have then also the physical information in not only the observations, because
Yeah, I think there are many ways of this. It's interesting, many ways of combining this. Yes.
Yeah, for this, I think we should not forget that the weather forecasts are delivered in operation with 3-4 hours delay.
Yeah, but that's why you can still use a past.
Yeah, but in the state of the art, I mean, there are also works where they combine measurements with NWP for the short term, for the next up to 6 hours. So they use the available NWPs as input to the model, together with satellite, together with spatiotemporal measurements. So at the end of the day, it's interesting to compare the different approaches.
Yes.
Or combine them.
That's actually not that you always need to have the same data. You have to have all the models and all the input data at the right time period. That's not, and it's quite an effort.
Yeah, I know.
For the case study you present there, so which is actually the model in the middle? Which one is it actually? Because it's in such small print.
Yes, that's an open. It's a solar steps. That's not even a machine learning model. It's optical flow and it's available for free. I mean, like you can just use it. And like the convolutional LSTM, the machine learning model is the top right, right? That's the one in the middle. There are two. This I think is a convolutional one, and this is a generative one. Yeah. Yes. Yeah. Good. Thanks a lot. Thank you.
Was that the
No.
last?
Helena.
Yeah, exactly. Last part of this session. It's going to be by Helena from
ENFOR.
Okay,
Yeah.
ENFOR.
Yes.
And also about ramps.
Also about ramps, yes, but more with respect to ramps in wind power forecasting ramps. Okay.
Yeah.
Is it? Yeah. Great. Great. Well, welcome everybody. My name is Helena Hansen, and I'm a forecasting consultant at ENFOR, a Danish energy forecasting company. And today I'll be talking a little bit about the advances in wind power ramp forecasting. And when we say wind power ramp forecasting, it's more about the wind power ramps and the output of, like, on an asset base. So looking more on the output of this wind turbines, how it looks like. Very briefly about ENFOR, we're a Danish energy forecasting company, and we forecast about 15% of the total installed capacity of wind and solar. And one of the services, some of the services that we have is, for example, wind power forecasting, which I'll be mainly talking about today. Quite briefly, wind power forecasting. I know that, we've been talking mainly about forecasting within on the meteorological perspective, right? About the uncertainties that we have there with the ramps, etc. And whenever we do wind power forecasting, we use these weather forecasts, multiple of them, in our WINFOR, which we call WINFOR model, which is our own model that forecasts wind power outputs. Okay.
We don't share.
Yes, and this is, I think, a lot of forecast providers have their own little model that does this forecasting. Yeah. I think it was the F, no? Or it was this one.
No, which one? This one, not this one.
No.
Can close this one also. Yes.
Yes, exactly. Yeah. Nice. Great. Yes. Exactly. It works great. So basically, we the model that we provide is this WINFOR which is our forecasting model, and it takes few inputs. So the NVPs, which we have talked a lot about today and yesterday as well. And then we also use a lot of the wind farm data to calibrate then the data, with, like the output of these wind parks with respect to how it behaves. And kind of with this, I wanted to show how important it is to have obviously accurate numerical weather predictions, because I mean, whatever uncertainty there is with respect to ramps, all these things gets directly feed into our model, right? So it's quite important for us as well as forecast providers to have accurate data. And that's also why we have we use a lot of different ones and combine them, because we want to kind of catch the different uncertainties that there is on the different spread. And generally, a few different power outputs that we usually provide is either point forecast, which is actually the most broad one. A lot of providers just want us to try to give them the best prediction possible, hoping that it has minimal, errors, and that it just basically predicts the perfect future. Obviously, this doesn't really happen. It's quite there's always some errors, some ramps, everything that we've seen. Therefore, some things that is quite useful to provide can be maybe these probabilistic forecasts and also scenario forecasting, which is quite essential for ramp forecasting. And these two are the ones that I'll be kind of focusing on today with respect to wind power ramp forecasting. If you want to change. All right, and for this ramp power forecasting, I'll be mainly talking about 4 different points. I think the font is a little bit different than on my computer, so you can't see it all, but I'll be talking mostly about, these 4 aspects. The first one being probabilistic forecasts and ensemble models. So whenever we produce these probabilistic forecasts, we also use this ensemble models using the spread kind of to adjust the probabilistic forecast that we have, right? We try to adjust the uncertainty based on the uncertainty that we have also with these NDPs. And the rest is also obviously based on historical data that we have from the farm. And we kind of use this, create these quantiles in that sense. One thing about this though is that, yes, you get a nice bandwidth, but you don't really get the progression over time of how these forecasts will affect the plant. And one thing that you can then create instead of having probabilistic forecasts is producing some scenario forecasting. So we have scenario forecasting are essentially just equally probabilistic outputs of these forecasts, which are I'm losing my train of thought, but they are based on this historically trained data, and are kind of fulfilling this data structure that we have historically. One thing that should be said about this scenario forecasting is that it has to be, what is important is that they are respective of time, right? It's quite important that we have this autocorrelation aspect, that they are time dependent, essentially. Because if they're all independent of time, we kind of just get some random, equally probabilistic output as well, but it doesn't really reflect anything, right? It doesn't really move with time. Whereas if you have these scenario forecasts, which are also respected of time, they all are likely events that are equally probabilistic. And this is essentially a stochastic spread that you can use, right, to determine the likelihood of these probabilities. But you can see here, okay, there's only 5 events, 5 scenarios. How likely is that these 5 scenarios will happen? Because it's, there's a lot of ramps you can see, it goes up and down. They're all equally probabilistic, but 5 events are quite sparse, right? So if you have to do something that's significant in any way, you kind of have to do a lot of simulations. So in our case, when we've worked with a client, we've done over 1,000 simulations, scenarios, in order to, and then just basically count it whenever there is a ramp that's relevant. Because otherwise you can't really determine any significant probabilistic out of it. Oh. And I wanted to just show you a real life case that we had. So essentially we have a client, which is a small TSO from a a small country which has very varying climate and increasing penetration of renewable energy, which we've seen the last few days. That means that they're very sensible to any errors in forecasts, errors in weather predictions. They actually gave us some requirements as to what do they want when they say they want ramp power forecasts. A thing that they defined for us was that ramp events are plausible changes in total production that have a likelihood of greater than 2%. Okay, it's a little bit of a broad statement, but basically, they want ramps that are above 2%, above a certain threshold. It has to be a change in of production above a certain threshold, and actually that lasted either 1 hour, 3 hours, or 8 hours. There was different requirements for them, basically. And it's because they obviously, as we've talked yesterday with the TSOs, is for production, for security of the net, things like that. And this is actually one way that the client wanted us to present, wanted to show how ramp power forecasting can look like, right? So you have these different ensemble members. You take, this is just one day, the dark one that they highlighted is just one of the ensemble models where one of these events have, and the blue lines are then ramps of 3 hours. So looking at how in 3 hours, how they develop over time. And then we map them with magnitude just for clarification, and then basically just plot them over time. And that's kind of a way to just show, okay, how does it move with time? And it's about power versus the ramp. So it's more about the change with respect to the plan, basically. To kind of accommodate for this, ENFOR did this scenario forecasting. We produced a lot of different scenarios, over 1,000, and did this, basically counted how likely are these scenarios, these ramps from happening. And then obviously when there are 1,000 cases, 1,000 scenarios, is the client able to handle these things? In this case, they were actually able to handle 1,000 cases, but then we would only basically send them the cases where the likelihood of that happening was above 2%. So it's more about this kind of planning that's interesting for them. All right, and if we look at a different way of looking at these scenarios, or a similar way, but from a different angle, we can see that we have this scenario forecasting. Again, it's the 5 ones that we had beforehand. And then we have the dark black line, which is actually a forecast that was day ahead. So like the planned forecast, what were they expecting to produce? If we then flip the forecast and look at these ramps with relation to the planned production, then you're actually able to see the magnitude of the ramps a little bit more, right? It's like then you have the ramps scenarios with respect to the plan. Yes, and that's actually essentially what we were sending them, right? It's like with respect to the actual planned production, what are we expecting? Yes, and finally, these ramp events probabilities. So out of the 1,000 scenarios, what was the percentage that these scenarios would happen, that these kind of ramps would happen? And this is a way you can plot it, where you see so 1 hour of regulation or 2 hour of regulation needs. What is the threshold of for example, that 5%, that there will be more than 5% that will have a probability of an up ramp, for example. So then you can look like, okay, in horizon 10, there is about 20% probability that more than 5% will need up regulation. So that's like a way to show ramp events. Right. And I think just to round off, I think it's a little bit short and sweet. It's just more, I just wanted to highlight that, whatever NVP uncertainty that we have, we're very susceptible to that. So it's great to see that there's so much advances within NVP accuracy, all these things, but yeah, so we're just we're susceptible to this, but nonetheless, extreme weather makes accurate forecasting all the more vital. We know this, but also for like on the production side, this is quite needed, right? Because otherwise there's a lot of these up-down regulations that we don't otherwise reflect. Yeah, and then just generally this temporal correlation is critical for accurate ramps. And I think I didn't highlight that enough maybe, but this temporal aspect is just important because we try to always get the latest information. And whenever we send these ramp forecasts, we do this in 15-minute resolution. So we send them data every 15 minutes. And it's usually maybe 5 days ahead that we've done this for the client. But obviously, yeah, I think the forecasts are just more accurate on the short-term level, right? Because we get the latest information, we get it both from the plant, from the NDPs. So time is quite essential in this case, right? Yes, and then just scenarios and quantile forecast capture uncertainty. Yeah, that's something that obviously the point forecasts don't do in the same way. All right, that was my presentation. Thank you very much.
Thank you for the presentation. One question, how do they use this forecast capability? So do they use them visually, the scenarios to know, okay, when a ramp will happen with what probability? Or do they integrate this as input to an optimization model that take decisions, I don't know, for the scheduling, etc.?
I'm actually not completely sure but what I would say is I think it's more on an operational basis. Yeah, so I think it's to see, they want to make sure that these kind of extreme ramp events, are they able to handle this? Are they able to accommodate for this need? So I think, for example, yesterday, Energinet was talking about this P10 and P90 quantile, where they have to be able to have these dynamic reserves. And I think it's a little bit to this that they're using it. Yeah, I think at least that's my guess, yeah.
Yeah, it's in a similar direction. I was astonished to hear that they went only 2% probability, and now hearing that it's a 5-day forecast.
Yeah.
Don't they drown in
things? Yeah. I think also one thing that I kind of understand that. I think one thing that there is that they also do this cluster analysis where they take these thousands of scenarios and then cluster them based on type of ramps events, and then they take one specific scenario as like a representative of this cluster. So then it boils it down a little bit to 8 different scenarios, something like that, with different likelihood events. But yes, it's a lot of information. I think, and it is more about this risk mitigation, I would say. But but I'm not exactly sure on the TSO side how they are handling it. Yeah.
I would be interested to know, did you actually do some verification on timings and magnitudes of these ramps?
I would have to pass on that, I think, because I wasn't the one who did this work. I want to also give credit to my colleagues, Henrik and Stig, but I can definitely ask them that and get back to you if, I can do that.
I need to write a mail just to you.
Yes, super, then you can do that.
Yeah, I think I like the scenarios idea also that you're using different MWT models. And my question is also following up on this. From using different models, do you run or like you have an idea by using it every time and so multiple time scales? Do you see that there are some models, for example, that produce more false alarms than others, or like more warnings than others, or like have a higher probability of detection than others?
When you see the models, you mean the NDP models, or I mean, with regards to NDP models, we run them through our WINFOR model. So we take these NDPs, put them into our WINFOR model, and then get this probabilistic outcome. So how much we use the different NDPs are actually based on their historical performance of these different assets. So I don't have the specific warnings on each of the different NDPs. I don't actually know specifically how which ones create more or less
historical performance maybe didn't before.
Historical performance, it's more based on the actual observed power from the wind plant compared to the forecast. So we put them into the wind farm model, look at how how the wind was, and compare it also to the physical power curve of the asset as well. So we're looking a little bit on how only one MVP will perform with regards to the output of the power plant, basically. Yeah.
Thanks. Very nice. Very, very interesting to see the different angles you take at the REMS forecast products. One that I'm particularly interested in is that caught my eye in your presentation is the imbalance scenarios. Did I get it right that you always referring to day-ahead forecasts there?
I think it's, yeah.
My question is, are you effectively forecasting forecast error REMS? REMS in the day-ahead forecast error could be going both directions depending on the actual wind power REM. Did I get that?
Yeah, I think with that, this was kind of this was an example of this case, right, with this client, that was what they were looking at. They were looking at the planned production day ahead. But of course, yes, there will probably be some inherent error, right, from the forecast. Yes, I think if you want a more detailed question, I also think that I'll have to ask my colleagues. I'm sorry about that, but yeah. But please send me an email about this afterwards, and we can definitely discuss. Yeah.
Very urgent. Last question.
Yes.
Okay, assuming that Energinet wants to make dynamic reserves estimation, and you provide them scenarios of the wind. So a lot of scenarios, the starting point is 10,000 scenarios. But this is not the only uncertainty. They have also uncertainty from PV.
Yes.
And probably another 10,000 scenarios. And of demand, and probably another 5,000 scenarios. And these scenarios have to be correlated, because wind production and PV production are correlated. You cannot have.
No,
so
that's true.
What happens in that case?
Yeah, I mean, that's a very good question, because obviously it's a big problem, right, with the computational, like how much computational power you have to take to do these things. And I think in this case, at least, what they did was a cluster analysis, right, where they had these clusters and basically they counted these scenarios and looked at, okay, the different scenarios, which ones were likely, or which ones were closer to each other, right, and basically counted the probability from the closer ones. Yeah, but obviously, as you say, it's a difficult task, right? Because we're trying to forecast something that has very low likelihood, but still has a very big impact on operation, right? So a lot of these wind farm models don't actually reflect these ramps, and I think that at least that was one take that we had on this. But yes, it's not a perfect solution.
Insight on this because, okay, I think the good thing is that the scenarios are not used as input to an optimization problem, because the reason why we started at some point in the state of the art to generate scenarios, it was because we had these stochastic optimization algorithms which use as input scenarios of the stochastic variance. Alternatively, the robust optimization, they use uncertainty bucket, and they are more based on quantiles.
Yeah.
So the problem is that we have seen that the complexity increases so much of these algorithms if you use more than 10 scenarios for each variable, that then automatically you have to apply scenario reduction methods. That's why there was finally a shift to the robust optimization algorithms, which are simpler. And I think if one day they decide to use this scenario in an optimization problem, then they ask you, okay, reduce that.
Yeah. That makes sense.
This is the very last one.
Thank you for the talk. I was wondering if you could say a bit more about the architecture. I assume you take a probabilistic forecasting architecture.
You mean with respect to what, to the
forecast model?
So just a classic wind farm model, or
Yeah,
So I mean,
kind of architecture it's using, there are several probabilistic models that one can use.
you mean, yeah, so I think I'm a little bit, I think with regards to the details, I think I don't know exactly if I don't exactly myself have all the details because I'm not sitting in the development team, unfortunately. But what I can say, at least for now, is that, I mean, it's mostly, it's like a mix between physics informed and stochastic modeling, right? So you have like the physics informed from the initialization of the power curve that you have based on where the site is, based on the capacity, the turbine, all these things. And then you also have the real-time data that you get from the park. So you get the real-time data and you get some schedules, curtailment, availability, and you try to clean this data as much as possible and basically adjust your model based on what's actually happening, right? So it's like a mix of the two. Yeah, that's basically how we do it. I think that the specifics, I don't know if I can actually disclose so much, but yeah, that's essentially what we do when we do power forecasting.
Thanks.
Thank you.
Just before us and the coffee break, we're having a few leftovers from the workshop that we wanted to fix. And that's the last 4 questions from Abhinav on the Slido. So if you could just get that one done, and then we go to the coffee break, and finally to the actual task meeting.
I'm sorry that I stand between you and the coffee break. You must be hating me. So I have these very general questions, so they're not related to too much related to my presentation anymore. And from the discussions in the last days, I think I have this feeling that they are relevant for quite a lot of us. So perhaps we can take a look at them, and then I could also share the results with everybody who's interested. I don't know how we do it in mails and so on, but maybe. So essentially, I wanted to understand what are the applications of forecasts, wind energy forecasts in particular, beyond day ahead. So I think this is the heading of the.
So there's 4 questions and you need to answer all 4 before you can submit your answer. So we'll just go through real quick. Maybe you can describe all of them and then.
Okay, so then, so you probably have some applications in your mind for forecast beyond day ahead, and you must be, but then on one side there are applications, but on the other hand, there are the products that are already available. So in this question, I want to understand if the products that are already available skillful enough to address those applications. And if they're not, it probably requires further development on the forecasting side, but the applications are already present, or if there are no applications at all and forecasts are already good enough. So that's what I wish to compare with these 2 questions a little bit. And then I want to understand how exactly you use these forecasts. So this is something that it was in the recent talk as well. So there is the point forecast, quantiles, scenarios, or some other forms. So how exactly would you use those forecasts for your applications? And if you wish to discuss, I would be very grateful if you have some use cases and you are open to discussing them in more detail. I would love for us to contact and talk a bit more about it in detail. And if that's okay with you, you can provide your email address here. Yes, so those are the 4 questions. Thank you. Maintenance, hedging, stocking up on fuel. Maybe if you're still at it and if you already have a clear idea, you could also perhaps in a bracket mention the horizon that application is relevant for. But if not, that's also okay. Storage management, reserve allocation. Yeah, so it's exactly that kind of thing. There it might be nice to understand at what horizon it's really relevant. Scheduling and maintenance, planning of different fuel supply and battery needs. Understand the battery optimization is usually done on day ahead level. I'm not sure if maybe we can discuss this as well. Aviation cost planning, maintenance. Hedging strategy, I assume that's something that can take advantage of seamless forecasts as well, something that was related to Albert's talk. Okay, thank you. Oh. Okay.
Is there not one more as it was?
So this tells me that there is some trust on the forecast, but then this.
I think the answer is it depends.
Quantiles, interesting. I think that's also the most interpretable sort of product that can be delivered and easier to handle, so to say. Ensemble mean, but interesting to see the ensemble scenarios being on the second number as well, because usually we do the skill scores and then we take the ACC as a skill metric and it's done on ensemble mean, and we focus a lot on that value. It's interesting to see that the use cases are for quantiles and ensemble scenarios more than the ensemble mean. Yeah, I think those were the 3 questions. Thank you.
Now,